Okay, so at this point, I'm going to go into lots of case studies for convolutional networks, and we'll see all the winning convolutional networks for all of ImageNet competitions, and we'll see how people actually wire up these convolutional networks in practice. Before I dive into that, I can take a few more questions regarding ComNets. So go ahead.
What is the intuition behind actually stacking the filters as opposed to like doing something like a combination, like linear combination?
So you're saying instead of stacking filters like one on top of another in terms of conv, you'd like to do something else instead?
Yeah, I was like wondering why stack as opposed to just throw another mathematical operation over them.
I see. It's just we like to do dot products because we know how to backprop through them efficiently, and it's just a very simple functional form. And so if you want to do dot products and you want to have a local receptive field and you want to do sharing so that you're not exploding with number of weights, so a lot of these design decisions make sense. I don't know what other simple mathematical functions you maybe want to use instead. So in practice, anything you can backprop through, you could put in a ComNet or into a neural net in general. So we use these functions because they happen to train efficiently and maybe partly historically, but I also have trouble thinking about what else you'd put in there. So conv layer is the main kind of workhorse of convolutional networks that's doing all the most important computation. Go ahead.
How do you represent the layers of like big depth?
Yeah, so these layers, layers of very big depth, like volumes of very big depth. So these volumes are all basically three-dimensional NumPy arrays, say. Or maybe if you're working in a bashed implementation, then these are four-dimensional arrays. And so it's just all these four-dimensional arrays you're operating over in your layer, and you're producing four-dimensional arrays or three-dimensional arrays.
No, I meant when you print them, like where does the image come from? Since it's so
So the input image is just a 32 by 32 by 3, say, array of numbers, right? And then the conv layer will transform that into a different volume. That's not exactly your question, but I guess I'm not understanding.
how you print the weights, the layers in between.
Oh, how am I doing this particular visualization? Or
Yes, how do you print the weights of the like intermediate convolutional layers?
oh, I see. Okay. So on the first layer, you can visualize the weights because they tie directly into the image. How do we visualize the later conv layers in their filters? Thank you. So there's a few ways we'll look into. I flashed a slide very early on. It's like 50 slides that I can't find it. Do you remember it? No? Okay, we'll find it. There's some techniques that have been developed over the last 2 years. So these visualizations are visualizing what the neurons are responding to, but they're not visualizing what those filters are. And there's no good way to visualize that, in fact. So in ComNet.js, I visualize them just by like still insisting on just like here's the weights, but you can't interpret them when you look at them because it doesn't make sense because they don't directly connect to the image, right? Okay, go ahead.
So in that slide you just showed, it seemed like the later layers show kind of more specific higher level features, but then it seems like if you're pulling down, it would be harder to represent those sort of complex shapes. Is that?
I see. Yeah. So you're saying that some of the filters later down, like say they respond to, say, little car wheels or something like that. When you do the pooling operation, effectively what you're doing is you're throwing away a tiny bit of spatial information. So once I've performed the pooling operation, I know that there was a car wheel somewhere in the 2x2 square or whatever that projects to back in the image. But I don't know exactly the position of that car wheel because I've thrown away some spatial information because I don't know where in this grid this 6 came from. So spatially, we've lost a tiny bit of information, but we still know there's a car wheel somewhere there. And so we are throwing away a tiny bit of information as we do every single pooling layer.
I think the whole idea of this ComNet is to like abstract information from high-dimensional information. You only abstract a label.
Yeah, that's right. So, I mean, to some extent, we're getting this image. We want to throw away some information at some point, maybe. Yeah. I mean, it's not really clear, but you want to eventually just get the scores out. And so we're just doing all this compute. Turns out that you can afford some invariances, sort of. You don't have to know the precise position of some of these things. And so the pooling layers throw away some of this information. At the same time, there are papers, we'll go into this, called, for example, is spatial information preserved in ComNets? And they study it, and in fact, it is. And so this almost seems like we're throwing away spatial information, but ComNets are still very good at precisely figuring out where things are in the input image. And so that seems like a paradox, and we'll go into that in a bit. Well, we have too many questions. Go ahead.
Is there ever depth reduction before the fully connected layer?
Is there ever depth reduction before the fully connected layer? There is. We'll go into specific use cases of sizing all of this. So maybe anything that has to do with sizing of architectures in practice, maybe save that for a few more slides. Go ahead.
If we have a lot of layers of convolutions, and each time we're sort of padding with zeros. Is there any problem with like the zeros on the, like, it's sort of like diffusing into the image? So like the values of the convolution products, like at the center will still have like, will be higher than like sort of the borders after a lot of layers.
Yeah, thank you. So you might say that, for example, these conv filters, they're used to seeing stuff. And at the edges, if you put zeros there, it's kind of like some of these filters might compute, say, the scale is slightly off because of the zeros, which normally you'd expect some ReLU activations or something. So it's true that maybe the statistics on the border are slightly different than in the center of the inputs, but we basically don't worry about it too much. But I do agree with you that it's kind of an issue. I haven't seen anyone like properly address it very satisfyingly. It's a bit of an issue because the statistics at the border, if we pad with zeros, might be slightly different than what you'd see in the center. Go ahead.
Does it make sense to initialize filters with like unknown kernels, like edge detection kernels? Or?
Do we initialize filters with some sensible initializations, like say specific edge filters? We don't. Just train it end to end. It's almost always these filters that have these edges. They pop out very clearly always, so it's not really an issue. It seems. Okay. Let's look at some specific examples because I think it's going to clarify a lot of questions as well. So let's look at first Linnet 5 from 1980s. I'm not going to actually go into a huge amount of detail here. You can see this is a figure from the paper. We received a 32 by 32 image. Then they had 6 kernels, 6 filters that were 5 by 5. So they used 5 by 5 throughout this architecture. So 6 5 by 5 filters, which brought it down to 28 by 28. And then they did subsampling layer, S2, which is subsampling or max pooling. So they subsampled it. And then they did 16 convolutional filters, again 5 by 5, applied at stride 1. And so they got 10 by 10. And then they subsampled that again. So you get 5 by 5, reduction by half. And then eventually they flipped to fully connected layers. So the architecture we would say is conv pool, conv FC, or something like that. And they use 5 by 5 filters applied at stride 1, and the pooling layers were 2 by 2 applied at stride 2. I don't want to dwell on this architecture too much because we have a few more interesting architectures as well. So we'll go into much more detail in AlexNet. So AlexNet is the architecture from Alex Ruchevsky et al. In 2012 that famously won the ImageNet competition by a big margin. So its inputs were 227 by 227 by 3 images. And it had this architecture here. This architecture, by the way, is cropped on the top. You can see that. That's not my mistake. That's actually from the paper. It's cropped like that in the paper. So what's funny is that when people give presentations on this architecture, it's always a cropped figure. And people are like, why'd you crop it incorrectly? And that's from the paper. Another thing to point out is it has this funky architecture where you have 2 separate streams. You'll see that it's kind of hard to see, but there are 2 separate streams that compute similar things. That's mostly a historical reason because Alex at this time, GPUs were not very good, not a lot of memory on the GPUs, so he had to split the convolutional network on 2 separate GPUs. So he had 2 separate streams of all these convolutional layers on 2 GPUs. But we're not going to worry about that, so we're going to talk about like a simplified AlexNet. Suppose we did not have that concern, and we just have a single stretch of ComNet. Okay? So let's look at the first convolutional layer, which in this architecture had 96 filters, 11 by 11, and they were applied at stride 4 over this input. What would be the output volume size in this case? So the width height are, I'm giving a hint. 55. What is the depth of the output volume after the first conv? 96. Awesome. So we have 55 by 55 times 96 because there are 96 kernels. What is the total number of parameters in this first convolutional layer? Maybe you can't compute that. I don't know. Okay, that is kind of difficult to compute, so I'm just going to give you it. I didn't expect you to do this in your head. So it's 11 by 11 times 3, because every one of these filters is 11 by 11 by 3 channels. There's 96 of them. It's roughly 35,000 parameters. One thing to note, by the way, is One thing to note, by the way, is when you look at this figure, you'll see that the input image here, it says 224 instead of 227. So Alex, when he describes this architecture in the paper, he insists that the images are of size 224. But if you take 224 images and you take them through 11 by 11 filters at stride 4, you don't get 55. So it's improperly sized. And this is kind of like a mystery that many people are always confused by when they read the paper. It does not work. The first layer should be 227 by 227. So we're not sure what Alex did. But when you read the paper, do not be confused, just like everyone else. this first layer should be 227 by 227, otherwise it doesn't work. So otherwise you can't get exactly 55 output. So I'm not sure exactly how he padded the input or something like that, but it's not described in the paper. Don't be confused by it. Okay, so after that we do pool 1. And so we take this conv volume, and the next layer is a pooling layer. It has 3x3 filters applied at stride 2. So what is the output volume size after the pooling layer? It's 27 by 27 by 96. Okay, good. Good. So there's many other... Oh, shoot, I gave away my... Oh. How many parameters are there? This is a trick question. Okay, there are 0. All right. There are 0 parameters in the pooling layer. Only the conv layers have parameters. So there's many other things in AlexNet. I'll actually put down the full architecture. So we have conv pool norm is a special normalization layer that used to be used at the time in around 2012, 10, and so on. Now we don't actually use normalization layers anymore. They were doing a particular kind of funny normalization operation that we don't use anymore because it doesn't actually give any improvements. So I didn't cover it, but there was a normalization layer at the time. So conv pool norm, conv pool norm, conv pool, and then fully connected 7, 8, and so on. And so you can see all the different filters. We had 11 by 11 in the beginning, but then flips to 3 by 3 filters throughout. And a lot of these conv layers here, for example, they apply 3 by 3 filters at stride 1 with padding of 1. So at this point, the image has been reduced to a size of 13 by 13 spatially. And then we're just doing all these conv operations on it without actually resizing the spatial dimensions of this input. So we keep it at 13 by 13 for a long time until a max pool. Then we arrive to a 6 by 6 by 256 volume at the end. And then we put a fully connected layer of 4,096 neurons at that. And then we do one more fully connected layer and the last few neurons. So in general, you'll see as we go through many of these architectures, it's just a sandwich of conv, pool, conv, pool, conv, sometimes pool, and then fully connected at the end, and then you have your scores. And so basically, we've transformed the image, the original image of 224 by 224 by 3. We see how it was transformed through a series of operations that are all differentiable into our class scores at the end, which in this case, we have 1,000 neurons at the very end because there are 1,000 categories in ImageNet. And so those are our class scores, and we backpropagate through all of this. Okay. One note I forgot to mention for the conv layers, when you do the backward pass, you have to be careful with that, right? Because the parameters are shared across, like as you convolve with the filters, all these neurons share parameters. So you have to be careful that you add up all the gradients across all those filters into a single weight blob, sort of. Now, in terms of conv architecture, what was interesting about it at the time when it came up is it was the first use of rectified linear units, or at least I would say definitely popularized it, at least in the computer vision community. It used normalization layers, which are not used anymore too much. It used heavy data augmentation. We'll go into that quite a bit. It really helps. What that refers to is you take your original image, and instead of just piping through that image, we're going to actually be jittering it spatially. We're going to be resizing it a bit, changing its colors a tiny bit. And so we're hallucinating additional training data. It used a dropout of 0.5, but it only used dropout in the last few fully connected layers. It used a batch size of 128, trained with SGD momentum of 0.9. The learning rate was 1e-2, and it was reduced by 10. Whenever the validation accuracy, as you're monitoring, whenever it plateaued, you'd reduce by a learning rate by a factor of 10. And basically, you'd reduce it once or twice, and by then, the network is basically converged and trained. Uses L2 weight decay of 5e-4. And so these are like rough numbers I'm showing you just so that you have a single kind of examples of what people use in practice in terms of these hyperparameters. And the performance on the ImageNet test set was at the end for a single convolutional network was 18.2% error. For if you form a 7 convolutional network ensemble, you get 15.4% error. So if you remember from last lecture, you're supposed to get 2% extra when you do an ensemble. In this case, we're seeing a bit better than 2%. So, the approximate rule. But yeah, so that's the AlexNet. So we're going to see some variations of this now. And I guess I should also point out that the number of filters, you can see that it went from 96 to 256 to 384, down to 256. And those are rough numbers you'll see. Now, in 2012, this was the winner of the ImageNet Challenge. In 2013, the winner was what we call ZFNet from Zeiler and Fergus. So this is also a paper that you can check out. It built on top of AlexNet architecture, but they made some modifications based on some experiments. And in particular, the big changes were for the conv1. Originally, there was an 11 by 11 stride 4 convolution on the first layer, and they found that that was too drastic. You're skipping way too much, and you had all these funny artifacts in the first layer. So they instead recommended that you do 7 by 7 filters of stride 2 instead of this. And so you're doing more dense computation on the very original image. And for the conv 3, 4, 5 layers, conv 3, 4, 5 layers here, they used larger filters. So there's more kernels in there, more filters. So originally this, and they changed it to that. And basically, based on their experiments, they found that this was a lot of the limiting factor here, is you want to increase these conv layers to get better performance. Another thing I also wanted to mention, by the way, sometimes you'll see people talk about extracting FC7 features from images. What that's coming from, actually, is from AlexNet, because he named these layers in this particular way. And FC7 is this last layer before the classifier. So people sometimes talk about extracting FC7 features. Even if they're not actually FC7, because they're coming from different architectures, people still sometimes use FC7 as just the last thing just before the classifier. And what I'm also not writing here is that there's, of course, ReLU layers after every single conv. So there's ReLU layers I'm not writing after every single conv and after every single FC. Okay, so that was that FNet. I'll talk a bit about the next, after 2013. Oh, and I should mention the top 5 error went from 15.4% here. It went down to 14.8% with this architecture. And the winner actually, so Matthew Zeiler, after completing this paper, where he got 14.8%, he created a company called Clarify. He worked on this a bit more, and he ended up with 11%. So that was the actual submission to 2013 ImageNet Challenge, had an 11% error. I'm also saying top 5 error, because that's how we evaluate ImageNet Challenge. We're not just looking at accuracy, but we actually allow the classifier to have a top 5 choice of what it thinks every image is, because there's 1,000 different classes, so we give it 5 chances to guess every single image. And so a top 5 error is saying, what is the fraction of images that you have incorrectly labeled in all of your top 5 choices? So basically, in your top 5, you did not get that image correct. So we're roughly not getting correct 14.8% at this point. Okay, so now we'll talk about VGGNet from 2014, again, to give you an idea of what these look like. In VGGNet paper, they had several architectures that they tried. What was nice and very interesting about this paper at this time was, instead of going kind of crazy with the architectural choices of how many filters and how many sizes and so on, there were way too many parameters in how you change the filters, what the sizes of the filters were. And so in the VGGNet, Karen Simonian and Andrew Zisserman, they just said, okay, let's, throughout the convolutional network, just commit to using 3 by 3 conv stride 1 with pad 1 and 2 by 2 max pool of stride 2. That's the only spatial dimensions we're using. So throughout the entire ComNet, we're just using these guys, and now it's just about how many you put in there. And so it turned out that a 16-layer model, I think this one, ended up performing best. I'm going to go into some of the details of this architecture. I'd just like to point out that their error went down from 11.2%, which was the previous year, and it got it down to 7.3% error at this point. I'm going to step through this architecture now. And this took me a while to create. So I went through and I wrote out all this, what is the size of the volume at every single intermediate step through the convolutional layer, through this D column here, which ended up working best in their paper. And you'll see that it's basically a sandwich of, we start off with a 224 by 224 image, and we do conv with a 64 filters, conv 64 filters, max pool, conv, max pool, conv, max pool, and so on. And so what we're seeing here is, I didn't even know where to start. Okay, so 64 filters, 3 by 3, 64 filters, then it goes up to 128 filters, then it goes up to 256 filters, then to 512 filters. So as the spatial size is decreasing, the number of filters is increasing. So spatially, the volumes get smaller, but we have more depth, right? So, so now we have 512, and then at one point you have a fully connected layer here of 4,096 neurons, as you see in an AlexNet, that is looking at the last pool volume. At this point, the image was shrunk from 224 by 224 all the way down to 7 by 7, but now the depth is not 3 color channels, but it's 512 kind of activation channels or something like that. So the total number of memory and parameters, by the way, if you add it up, turns out that the total memory here, if you add up all the numbers, is 24 megabytes. If you're using floating points, then each one of them is 4 bytes. So that ends up being 93 megabytes of weights. So 24 million at 4 bytes is 93 megabytes of memory of intermediate activation volumes. per image when you just do forward pass. So that's just maintaining all of this stuff in the memory because we need it when we do the back propagation. And so just to represent that image, all of its forward pass is 93 megabytes of RAM. And that's only for forward. For backward pass, we need also the gradients. So we would then end up with a rough footprint of about 200 megabytes per image, just to give you an idea of what the footprint of some of this computation is. And the total number of parameters is 140 million at the end when you add up all the parameters throughout this. So there are some fun things to note about the asymmetry between where all the memory is and where all the parameters are in the network. Okay? So in particular, you'll note that most of the memory of this is actually in the very first few convolutional layers. You've taken 64 kernels and you went through the image and you ended up with 224 by 224 by 64. And so you end up with 3.2 million numbers at that point. So quite a lot of stuff to maintain here for that single image. And so all the memory is here in the early conv layers, but all the parameters are here in the first fully connected layer. Okay? And the reason it's here is because we have a volume of 7 by 7 by 512, and there are 4,096 neurons looking at a fully connected manner at the pool layer. So you end up with a 7 by 7 by 512, 4,096 times, not counting the biases. So you end up with 100 million parameters just in that layer alone, the first fully connected layer. So that's not ideal. That's why you just accumulate a huge amount of parameters. What we found recently is that you can actually get rid of these fully connected layers. And you'll see that in some of the later work, where instead of using fully connected layers, people now like to use average pooling across this volume. So we'll see this, I think, in the next few architectures. But what works relatively well is the following. You have a 7 by 7 by 512 volume at this point, and instead of doing fully connected on this, you transform this into a single column of just 512 numbers. And you do that by doing average pooling across the full thing. So you do average pooling this way. So every single number in the output is a result of averaging 49 numbers in here. So you take those activations and you just average across, and you can use that instead, and it works almost as well. So you can save yourself a lot of parameters. So that's a trick that I think they actually used in GoogleNet, which is my next slide here. So this is GoogleNet from 2014. It's starting to look a little funky. So a VGGNet has this very simple, just linear structure. So in here, they're trying to complicate it. So the key innovation in GoogleNet was they introduced what we call an inception module. And even though this looks kind of funky, it's just a sequence of inception modules, just one by one. And I don't think I want to actually go into too much detail on the inception module right now. Well, maybe, yeah, I don't think I want to do that. But I'll just point out that the winner was the winner of 2014 challenge. It had a 6.7% top 5 error. So if you remember, original AlexNet was at an error of, where are we? 15.4%. So we've come down quite a bit, and we're now at roughly 6.7%. And the GoogleNet, you can go through this in a paper. I don't think I want to spend too much time on this. They have these inception layers instead of convolutional layers. What I'd like to point out, though, is you'll see here at the very end, you still have this volume of 7 by 7 by 124 in their case instead of 512. And then they, instead of doing fully connected layers, they do an average pool here. And so they reduce 7 by 7 124 to just 1 by 1 by 124. And so they save a huge amount of parameters there. So they get away with this entire architecture working really well at only 5 million parameters compared to a VGGNet, which is 140 million, or compared to an AlexNet, which is 60 million. So you end up with much less parameters, slightly bit more compute, but a much better accuracy compared to AlexNet. Okay, so those are some of the trade-offs. They were really trying to, in this particular work, try to reduce the footprint in both the memory and the compute. Question?
How much does accuracy drop off if you do top 3 or top 2 instead of top 5?
Yeah, thank you. So you're just trying to get a sense of the scale of these. So I think 5% top 5 error is roughly 20% top 1 error. I don't know the in-betweens, but that's roughly the conversion. Okay, so that was GoogleNet in 2014. I should mention that they won the ImageNet challenge, and the VGGNet, it didn't win. It had a slightly higher error, but you'll see many people use VGGNet instead of GoogleNet sometimes because it just has a much more nicer and uniform architecture. It's just easier to think about. And so in my own work, I usually use VGGNet as a default as well, but some people also use the Inception. Go ahead.
What's human level performance?
Good question. So we'll get to this, I think, maybe in a later lecture. Human level performance would be at about 5%-ish. And this is some of the experiments I've actually performed, and we'll go into that in later lectures. But around 5%, but if you take an ensemble of humans and you train them for a long time, you can get down to maybe 2-3% or so. Is my estimate, but we'll see that in a bit. Okay, so these networks are working very well. And you'll see ResNet, by the way, the winner of 2015, which is, I think, my next slide. So 3.6% top 5 error, okay? So this is residual networks from Microsoft Research Asia, work by Kaiming He and colleagues. And they did not, in fact, just win ImageNet 2015. They won a whole bunch of competitions at the same time. So all of them first places in a whole bunch of just very important competitions here. And it's with one architecture, and so that was very interesting, and I'm going to tell you about it now. But 3.6%, just wow. They had this graph. I'm taking some of his slides. You can look at the history of ILS-VRC, which is short for ImageNet Large Scale Visual Recognition Challenge. So in 2010, we had all these different feature types. In 2012, we had the AlexNet, so we jumped quite a bit down. And then we saw progress with the ZFNet. Then we saw progress with VGGNet and with GoogleNet. And now we're up to 3.57. And you can see that the layers basically just go up and up and up. So more layers works better, apparently. But one thing you have to be careful with, as he pointed out in his slides, is if you just try to do the naive thing, what he calls plain nets. This is everything I've explained to you so far is what he would call plain nets. They propose these ResNets, and I'll explain to you in a bit what that means. Now, what turns out is that you have to be careful with how you increase the number of layers. If you just do it naively, it turns out that it doesn't actually seem to work very well. So say you take CFAR 10, and you have what we're looking at here is the solid is the test error, but the dashed is the training error, okay? So let's look at the training error. And what happens as you train these layers is the 20-layer model is getting very good training error, and then a 56-layer model in red is getting a higher training error. And that makes no sense because the 56-layer model is a much bigger capacity model. So how can it possibly be doing worse at training error than a 20-layer model? So what this seems to indicate is that we just can't seem to, with the current techniques, maybe we're not good enough at optimizing these layers right now. So ResNets, in contrast, as you scale up the number of layers, you just always see a consistent improvement in both the train and test error. And so basically, all this is saying is you want a lot more layers, but not in a naive way. You want to do it in a ResNet way. And so we'll see what that is in a bit. So this is just a visualization of, this is the ResNet, 152 layers. So the VGGNet here was 20, so it basically dwarfs all the other previous architectures. Just to give you an idea about the scale, and we'll go into computational considerations soon, but you want roughly 2 to 3 weeks of training time on 8 GPU machine. So if you guys are not getting some good numbers sometimes working on your laptop, then don't feel too bad, because this stuff just takes a while to train. And even though it's 150 layers, it's actually faster than a VGGNet, which is quite interesting. So the ResNet, roughly the way it works is, here we have a plain net, where you take an image and you have a conv pool, and say conv, or something like that. In a ResNet, what we're going to have is these funny skip connections, okay? And so, in addition to this pass, where we're strictly just like transforming every single volume to the next volume, we're going to have these skip connections. And the way this looks like, oh, and I just have a note here saying that it's kind of interesting that you take a 224 by 224 image, and you apply a single layer of filters, and then you pool right away. So you've compressed the spatial size by a huge factor. By a single conv layer, you're at 56 by 56 spatially. All the other 150 layers are only operating on 56 by 56 array spatially, which is quite amazing that you can pack so much information into such a small volume. And that you can do so well on ImageNet with just that amount of spatial resolution almost. So the way ResNet works is as follows. And we're going to, I think, go into much more detail on ResNet, and we might actually give it to you for assignment 3, but we're not sure. Okay, we might fold it in.
I'd like to point out just how recent this stuff is. ResNet literally was presented in December at a conference. So this is like very, very recent research.
Yeah, so this is quite new. So we're not sure actually if it works. We're going to see if it works for our assignment. And if it does, then you guys will implement it. So the way this works is, in a normal plane neural network, you have some function h of x that you're trying to, say, compute here. In a normal neural network, you would transform your representation. So you have a weight layer, you get some new representation, you threshold it, and so on. a sequence of steps. In a residual network, what you do is your input flows in, but instead of computing how you transform your input into h of x, you're computing what to add to your input to transform it into h of x. So this two-layer neural network in here is just computing a delta on top of your original representation instead of just a new representation right away and just discarding all the information about original x. So this is a ResNet module. And what's nice about this is you're computing just these deltas to these x's. And so one way to look at why this might be nice is if you think about the gradient flow of backwards through these layers. In here, the gradient has to kind of go through all these weights and backprop through them. But in here, the gradient flows in through here. And since you're doing addition, remember addition just distributes the gradient equally to all of its children. So part of the gradient will flow through this part, but it will also just like skip over that part and just flow here. And so if you think about this architecture here, these skip connections allow your gradient from all the way here on the 150th layer of the softmax. Those gradients just skip through and right away feed into this conv layer here intuitively. And so basically right away you can train right away very close to the image, and you can right away train this little layer here that's doing maybe some simple statistics. And then these guys in the middle will just learn how to add to your signal in between and to make it work out at the end. Another way that this is explained is that this layer is basically, by default, you're doing an identity operation, and then this thing is just computing a delta on top of the identity. And so it just makes it nicer to optimize. That would be the rough intuition here. Now, in terms of how they train ResNets, just to give you an idea about, again, the hyperparameters that people use in practice, they use batch normalization after every single conv layer. So there's many conv layers, many batch normalizations everywhere. They use the Javier over 2 initialization. If you remember that the paper that proposed this over 2 initialization that I talked about when you use ReLU layers, that's actually the same person, Kaiming, that proposed that initialization. They use SGD momentum with 0.9. Learning rate is 0.1. You'll recall AlexNet uses initial learning rate of 0.01. The reason you can get away with a slightly higher learning rate, I assume, is because of the batch norm layers. They usually allow you to do that. So a bit of a bigger learning rate, and then divide by 10 anytime the validation error plateaus. Many batches of size 256, weight decay of 1e-5. So these are relatively standard. And they did not use dropout because the paper in batch norm, the batch norm paper claims that if you use batch norm, there's less of a need for dropout. And so I'm not 100%. I don't have first-hand experience with this, but they did not use dropout either. Okay, were there questions about question?
Do they train weights for the length of the skip step?
So there's no weights in the skip step. Or rather, there are, but not at this level of abstraction. Sorry?
Wouldn't it make sense to have a lambda there?
Do you want to have weights in this skip layer here?
Yeah.
I think what's nice about ResNet is, like, suppose this is just an identity where it just flows here. If you think about the backward pass, it's very clear that if this was exactly identity operation, then the backward pass gradient would just skip right through all these layers exactly and get all the way to the first conv layer. So that's like a nice desirable property. And the reason that these networks intuitively maybe don't work is because you're making them go through all these intermediate processing, and the gradient signal just gets all, I don't know, lost or diffused or something weird happens. Not 100% sure. And so that's nice. That seems like a nice property to have. Not to put in too much compute, but to put in lots of compute, but as an optional compute. Like this compute can come in later during the optimization process if you want to think about it that way. Good.
So it seems like without the ResNet module, like, intuitively we might think adding more layers increases performance, but that wasn't the case. What about increasing the spatial dimensions of your layers? Does that always yield an improvement, or?
Yeah. So you're asking about increasing the spatial dimensions instead of the number of layers or something like that. Like, where do you allocate your capacity? You have some finite budget of, say, GPU memory, and now you want to know, like, what the trade-offs are. So it's kind of surprising that in ResNet they take a very rapid reduction in size, and then they pack all of their capacity and, like, in terms of memory, into getting more layers. And so I don't know how thorough they were with thinking about these trade-offs or with their experiments. I have no idea. But in this case, they seem to go for much more depth at a cost of some spatial resolution very, very early on in the network. Okay. Yeah, you had a question?
How do you know when it's converged. Like decide, oh, it's converged, so I stop training.
How do you know when the network is converged? So it's never fully converged, but at some point you stop caring because it's been 2 weeks and you're just tired. There are some subtleties that make it work a bit better. I have to skip through this through interest of time. Using one-by-one conv in clever ways, as we saw in GoogleNet as well. I'll skip this. Okay, let's skip this. We only have 5 more minutes, so I want to catch some questions, but I also wanted to mention that this morning you may have seen case study bonus here. You may have seen the DeepMind's Go playing network. And this was on the cover of Nature. And so that's pretty impressive. They're playing Go, which is supposedly harder than chess. And this is ComNet's playing Go. And the way that works, if you go into the Nature paper and you go down to the details of the experiment, you'll find the section that identifies the policy network. The policy network is basically trying to identify promising moves. So it looks at the Go board, which is here a 19 by 19 array, and it's trying to put this through lots of conv and trying to figure out where you should place the next stone, okay, black stone or white stone, on this grid. And so if you look through this, you might by now be able to recognize some of the keywords and actually piece together the architecture. So the input to the policy is 19 by 19 by 48. It's 48 because they compute, I think, 48 different types of features that have to do with the specific rules of Go. And so it's not the raw array, which would have been much nicer, but they compute some kinds of features on every single position here. So 19 by 19 by 48 input, consisting of 48 feature types, and then they do convols, kernel size 5, stride 1, applies rectifier. Anyway, so I'm just making the point that you can basically read some of this and you can distill what the architecture roughly is. And so I wrote it out here. And so you start out with this input. They do 5x5 filters, stride 1, pad 2. So they preserve the spatial size. And then they do 3x3 filters, pad 1. So again, they're preserving spatial size at 19 by 19 for a long time. And then at the end, they have just a little 19 by 19 array that is telling you just how promising every single position is to play in next. And so that's the main policy network here that is doing a lot of heavy lifting in playing Go. It's just a large ComNet, and you train all those layers. And they train it on some human data and also some self-play data where the network plays against itself. And so that's pretty impressive that they can do that, and it's ComNet's doing all of this. So summary, we have these conv pool layers. There's a trend towards getting rid of the pool and fully connected layers. We're eventually going to end up with networks, I think, that are just purely conv. And the way you do spatial reduction is by doing stride 2 convolutions instead of doing max pooling. There's a trend towards smaller filter sizes, like 3x3, but having many more depths, many more layers. But a typical architecture for now looks like conv relu, sometimes pool, and then fully connected layers maybe at the end, and some softmax at the end, and some guidelines based on what you've seen. But recent advances, I think, are kind of challenging this paradigm. Like ResNet and GoogleNet, they kind of play with the architecture a bit, and it's a little more funky than just stacking these layers in a sequence. And so that's the summary. I have 2 more minutes, so I can take like 1 or 2 more questions if there are any. Go ahead.
So after you've trained a network, what's the trade-off? What's the computational performance of Linnet 5 versus all of the others, including GoogleNet, as far as taking the image in and getting the output out? And then is there just generally a trade-off between that, or is that not really taken into account at all there?
So you're asking about the computational performance in terms of like a runtime?
Yep.
From Linnet to all of these other networks? Yeah, good question. So Linnet was much, much smaller. I don't have the exact ratio, but it had many fewer filters, so you'd expect it to be quite fast compared to some of these. So ResNet apparently is faster than VGGNet, which is impressive. I don't know exactly. I can't remember. What is VGGNet forward time for like a batch of images? I don't have it like off the top of my head.
It's pretty slow.
Pretty slow? Yeah, what is the forward pass? It's on the order of like tens of or hundreds of milliseconds, somewhere there, basically, on a GPU. You can run an AlexNet on your phone in almost real time at about 10 hertz. That's roughly also a way to think about it. Okay, cool. So we're done. Thank you.